Welcome. This is the third video of a series on drawing shear and moment diagrams using graphical method. So in the first video we'll learn about what is graphical method, what are the graphical relationships between the load, shear and moment. And the second video we kind of seen a simple quick example of a beam that's simply supported and subject to uniformly distributed load. So now we'll see here a little interesting example with more challenging loads. So this beam here is supported at A and B. A is a roller and B is a hinge, so I'm kind of showing right away the reactions. There is a distributed load over the first 20 foot. The load here is 5 pound per linear foot, 5 PLF. And then the load stops after that until there's a point load of 20 pounds, and then nothing until the support at B, and then there's a cantilever part of the beam that supports 35 pounds. So the goal is to draw the shear and moment diagrams, and of course in such complicated beam we would prefer to use the graphical method compared to the equations method. So the graphical method is really quick to draw the diagrams of shear and moment. So before you do that, you have of course to figure out all forces applied on the beam. We're given the loads, but we're missing the reactions, so you have to find the reactions of the beam. So kind of doing this task on your behalf, kind of figure out the from equilibrium, the reactions at A and B. I highly recommend that you do this on your own, figure out the reactions at A and B. And I also named here some points of interest. So whenever on the beam there's a change in the load, what we call the discontinuity point, I gave it notations here, C, D, and E. So to start, we have to start with V, the shear, and then we will use the shear diagram to draw the moment diagram. So I start with the shear from the left, and I see here that I start with 0, but once I hit the, right away I had the reaction in A going up, so I jump where the value of the reaction 68.7 positive. And then also I know that I'm gonna draw the shear diagram and trying to figure out what will be the next point of interest for me, and that will be the point of discontinuity going to the right, which I will hit here, point C. Between A and C, I want to calculate the difference in shear. So I can use the area under the load curve. I have here a distributed load. So I can calculate this area AW, which is equal to WL. It's a uniformly distributed load, just this area of this rectangle. So it's 5 times 5 PLF times 20 foot. So that's 100 pound. That's a positive area load. Load area, sorry, that's a positive load area. But remember, there is a negative relationship between the load and the shear. So this means that I'm dropping from 68.7 by 100 pounds. So this means that VC is equal to VA minus AW. So I'm dropping to negative 31.25. Now after that, I look at what's my next point of interest. Discontinuity point next to me is D, and I can see here between C and D, really there is nothing happening here different in terms of the load. It's just, you know, a segment of the beam that feels no loads. So this means that my shear goes straight horizontal until I hit the load 20, because I'm moving from the left to the right. So if a load goes down, I hit it, and it's a point load. 20, I go by 20 pounds downwards from negative 31.25 to negative 51.25. Next point of interest is the point of reaction, B, and I will go straight horizontal to point B, and then I hit the reaction 86.3, so I jump by this value to now 35. Nothing happens between B and the next point of interest, which is basically the end of the beam, and I go horizontal here, constant value of 35, because W is equal to 0, so 0 slope, so 35 horizontal until I hit 35 load which brings me to equilibrium zero shear at the end tip of the beam. Smiley face. That's a good check for us here that we added up all these delta shear and we started from 0 at the left, we ended with 0 at the right of the beam. Now once I have the shear diagram, I will use it to draw the moment diagram. And I start from the left also, and you start with 0, and I see that MA will be equal, stay 0 because there is no fixed support at A, there is no point moment load at A, so it stays like that. And I look at what would be the next point of interest for me. I would say maybe C is a discontinuity point. That's the next close to me, so I will consider it. But remember, it's always a point of interest where the shear becomes 0. A 0 shear refers to a 0 slope for the moment diagram. A 0 slope generally refers to the maximum or minimal value. So here I'm creating a new point of interest, which is this intersection point of the shear diagram of the axis. And I want to find here the x distance that makes shear value equal to 0 if it starts with a value of 68.7, and I'm dropping by 5 pounds per linear foot. That's a simple linear algebra problem. So I'm dropping from 68.7 divided by here the rate of drop, 5, you end up with you're dropping to 0 at distance 13.75. So now this point of interest here, I want to calculate the difference between the moment between A and that new point of interest, that 0 shear interest, point of interest. So how to find this delta M, it will be by calculating the area under the curve, or this triangular area, and it's equal to half of the base, or the height here, 68.75 times the base 13.75. That will give us this value, 472.6. It's a positive value, positive shear values here. So I'm jumping or increasing the moment from 0 at A to that 0 shear point at distance x here. Now how to connect between these 2 points? At A, I have a big value here of the shear, a positive value, so that's a positive slope here. And then I have a 0 shear at distance x, that's a 0 slope. So now you can see I'm connecting with a parabolic shape with changing slope, and the slope here is decreasing from a high value to 0. What will be the next point of interest? It will be C, and I will calculate here A2 to be the area under the curve between that x distance point to point C. And A2 is a triangle, and you can see here that I'm using that 13.75 distance deducted from 20. That will be the base of the triangle times the height of it, which is, remember, when you deal with the area under the shear curve, you have to use the sign of the shear value. So I have here negative 31.25. That will result in a negative A2 value, which means I'm adding this delta value to 472.6, and it's negative, so I'm dropping to be 374.9. How to connect between the points? Starting with a 0 slope to a value of slope that's equal to the shear value negative 31.25. So I end up with kind of this parabolic shape. And then what would be the next point of interest? It's point D, so I'm calculating A3, and just a rectangular shape, so the area A3 will be equal to negative 468.7. So this means I'm dropping by negative 468.7 from C to D. So that will bring me to a negative moment value of negative 93.8. And then the next point of interest at point B, so I'm calculating A4 for that rectangular shape, and I will find that A4 to be equal to negative 256.25. So this means I'm dropping more in the negative, and you can see the rate of dropping here is increasing. So the slope of the first line between C and D is smaller than the slope of the line between D and B. Why is that? Because the shear value between C and D is negative 31.25 is less than the shear value, the absolute here, I'm talking about the absolute value of 51.25 between D and B. So the slope here is increasing. And then the next point of interest will be basically the last point, point E. So I'm calculating the area under the curve A5 between B and E under the shear curve. Calculating this area, that will be 350 pound-feet by multiplying 35 pound times the distance 10 feet. Which means that I'm adding this positive 350 to the negative value of negative 350 moment at B, which brings me to a 0 value of moment. And I don't have a moment reaction at the end, so it stays 0. 0 value means that's good news. That's my check here that I have a correct solution. So, amazing, right? Graphical method, you end up with these two diagrams in what? Less than 11 minutes. So it's not an easy beam. It has different loads, different cantilever parts. So it's not an easy beam, and you end up with this solution in 10 minutes. So that's great. So this is why graphical method is really amazing. We're using here our understanding of that graphical relationship between load, shear, and moment to draw the diagrams here. And by looking at the beam here, I can see now I can get the values that will be input to the design of the cross section of the beam. So I know now that the maximum shear developing in the beam is equal to 68.7, what's the reaction at A. And also the critical section for moment is happening at somewhere between A and C, and it's equal to 472.6. That's absolute moment value. So I hope you like this example here. I highly recommend that you try more examples on your own. In the lecture, I provide examples to try it yourself and also the solutions. But try yourself the problems before you check the solutions. So thanks for watching and take care.